Okay, welcome to Chemistry 111, Experiment 9, Determination of the Solubility Product Constant of Calcium Hydroxide. Compared to the previous labs we've done, this one may be fairly straightforward. Now, before we begin the lecture, when you arrive in the classroom, we'll be shaking the saturated calcium hydroxide solution for 5 minutes. This should save us all some time. So you should see a container with a saturated calcium hydroxide solution. Really, I think what it is that it just simply has excess calcium hydroxide in it. So the liquid above the precipitate is by definition saturated. To make sure it's saturated, we're going to actually shake it for 5 minutes, then let it settle. I'm sure it takes a while to settle, so while I'm giving the lecture, we'll let it settle. So do that when you arrive in class. The purpose of this experiment is exactly what the title is, to determine the solubility product constant known as the KSP of calcium hydroxide. Calcium hydroxide is not very soluble in water, so it's a good one to test. We'll find out how much dissolved by titrating the hydroxide that did dissolve with an acid. We'll run the numbers and we'll come up with the KSP. This is far more precise than trying to dry the precipitate and measure it precisely, since it can be hygroscopic and getting all the water out can be a pain in the neck, and so this is what we will do. Here's the background. Calcium hydroxide is slightly soluble in water, and here's the equilibrium. It looks like there should be a closed parentheses right there. Calcium hydroxide as a solid. Notice that there are 2 hydroxides for each calcium. Exists in equilibrium in a solution with its dissolved ions, the calcium 2+ ion and the 2 hydroxide ions. Notice that the concentration of the hydroxide is twice the concentration of the calcium once it dissolves. Every substance that dissolves has a known solubility product, and people usually use it for the ones that are sparingly soluble, like this one, and they define it as the concentration of the ions raised to their coefficients. So since the coefficient for calcium is there's only one of them, but there's 2 hydroxides, we square it. So if we can get the concentration of the hydroxide, we're good, we'll square that. And we know that the calcium hydroxide, the calcium concentration is simply half the hydroxide concentrations. After all, there are 2 of these for every one of those. So this should be pretty straightforward. Here's the general procedure. Now, compared to the procedures I've been giving you before, I'm getting a little more generalized because we've done a lot of titrations now, and some of this should be fairly straightforward. I hope I don't have to mention anything about preparing the burette or any of the sort of general techniques that we've been using. So here's the general procedure. Consult the manual for the detailed procedure. Here's the 1-sentence procedure. We'll titrate a saturated solution of calcium hydroxide to measure the hydroxide concentration. From there, we'll get the calcium concentration. We'll plug it into the KSP. We know this. We know this. We'll find out what the KSP is. Bada bing, we're done. That should be squared. This should be 2+ raised. There's some little details here that we'll need to fix. All right, here it is in a little more detail. Shake that saturated solution of calcium hydroxide for 5 minutes before we begin the lecture and let it settle while the lecture is going on. Prepare a 0.1 molar hydrogen chloride solution. Now, the details are given precisely for how to do that, so you don't even have to run any numbers. Just go ahead and follow the directions, and you'll get 200 mils of a 0.1 molar HCl solution. That's what we're going to titrate the calcium hydroxide with. Notice this time we have acid in the burette and not base. Now, we've made this thing by hand. We know it's about 0.1 molar, but if we're going to get good data, we better standardize it and find out exactly what it is. So, you will be given some highly precise standardized sodium hydroxide solution, and we're going to titrate your HCl solution that you've made to come up with more significant figures, more precision for its exact concentration. Now note that we haven't actually done the experiment yet. We're just trying to make a nice, precise HCl solution. So you'll have the sodium hydroxide in the burette, you'll drip it into the HCl, you'll use an indicator, and you should be able to precisely measure the concentration of the hydrogen chloride. This is simply a matter, since everything's 1 molar, everything is a 1-to-1 ratio, Just the molarity of the HCl times its volume equals the molarity of the sodium hydroxide times its volume. And if you think about it, you know 3 of those 4, and we'll be able to get a more precise value for the molarity of the hydrogen chloride. So that's how you do that. Now, once this thing is standardized, we can use it to titrate the saturated calcium hydroxide solution. So that will go into the Erlenmeyer flask that you're titrating it into, and you'll have the HCl solution in the burette. Don't forget to pre-treat your burette to make sure that it is conditioned and will not be modified by the glass itself. And drip that stuff in. And note here, I'll point out this friendly reminder here. You'll be using a bromocresol purple in the calcium hydroxide solution. That should change its color, right? I'm guessing to purple. And when it goes acid, because we've got a base in there, which is kind of backwards how we usually do it, it will turn yellow at that acid endpoint. So look for dripping it in, purple, 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 and then suddenly yellow, bing, you're done. And do as many trials as they say. And once we've done that, we've precisely titrated our saturated calcium hydroxide solution with the HCl solution, figure out the concentration of hydroxide using the exact same formula, the molarity of the HCl, which you know precisely, times the volume of the HCl, which you had to drip in, which you should know precisely, will equal the molarity of the calcium hydroxide, which we'll be solving for. That's what we don't know, times the volume of the hydroxide. Well, that's how much we put in the Erlenmeyer that we dripped it into. So you know 3 of the 4, get the concentration of hydroxides, and give me the following calculations. 1, the molarity of the HCl stuff that you standardized, and do it for each trial, then take the average. That's your second calculation. Just take the average. The third one is get the hydroxide concentration that we just mentioned up here. That's very important. That's really our only piece of data that we're going to use to calculate KSP. Same calculation, M1V1 equals M2V2. Solve for the molarity of the hydroxide. And then 3, from that, get the calcium hydroxide. Note that the formula is calcium hydroxide. Note that there are 2 hydroxides for each calcium. Now you can plug into the KSP, which is equal to the calcium ions times the hydroxide ions squared. Friendly reminders, read the burettes to 2 decimal places. The bromocresol purple turns yellow at the acid endpoint, and we will be filtering that saturated solution somewhere in the directions here, just to simply make sure that there's no precipitate present, and remind me that I will be demonstrating that filtration. All right, enjoy this lab.